This button? Yeah, there we are. That's really loud. I feel like Madonna on like the Vogue tour. So, this is really loud. Can everybody hear me? Also a really loud talker. That's me, Rick Waldron. You can see me yell about things and get excited about things here, or follow code things here, and find out more about NODEBOTS at those places. I'm going to go ahead and keep with the promise I made earlier to screen record. All right, we'll get things started. So, I work at Boku. T-shirt, right? I also started a project about January or so called Johnny 5. Johnny 5, essentially the goal is to be a framework of sorts for programming hardware, robots, Arduinos specifically, with JavaScript using the Node.js platform. How many people were here, were at NodeConf in Portland? At least a couple people? Alright, well, unfortunately for the rest of you, you'll have to watch my talk online there because I'm not really going to give much background. In fact, I'm going to jump into today's topic, which is how to propose to your girlfriend with a robot. As you can see, this robot is going to turn around and present a ring. Right? Fantastic. And she said yes, so it was right? Success. Just kidding. I'm actually here to talk about how I taught NodeBots how to walk. For those of you that were actually at NodeConf, you probably remember that I was primarily talking about async input. Essentially, you have sensors and various pins that have input. They're accepting information from the real world in real time, and they're packaging these pieces of information up into packages that are sent down a serial line, bit by bit by bit, and there's a protocol called Fermata that parses it and then says, all right, we need to do X with Y data and B with A data, okay? That's sort of one direction of the flow. You want to keep everything asynchronous incoming, but you also need to consider asynchronous output. And by this I mean, there is a legacy, so that begins with mechanical engineering, and then further on into hardware engineering with microcontrollers and so forth. Across the board, basically anything that has a clock and considers data and runs an event loop is in itself intrinsically synchronous, because it exists in the real world, right? In the real world, I am actually standing here, and I'm actually walking across stage, and I'm taking time. I'm using up time in my life to do this. A piece of hardware uses up time in its life to do things that you program it to do. So, if you think about it in these terms, when you have a piece of hardware that's running a constant loop over and over and over again, it just says, what's going on during the loop? Let me react to that. Or let me send out signals that say, this motor, turn it on. That one, turn it off. Whatever you have to do. Each instructions, they take time. They are async, right? Entirely synchronous. So, what ends up happening is when you have sequences, which are essentially do a thing, and then do another thing. But only do the next thing after I'm done with the first thing. For example, animate a character across an LCD screen, right? This is going to go from here and then back and forth. It's going to appear to be running. What this is doing is it has an interval that says, draw to this column and row. Draw to this column and row. Sorry, that's me slowing it down. But you get the idea. Wait. There's always this concept of do a thing and then wait. Now, whether or not that wait time is significantly shorter or longer is arbitrary. It doesn't matter. What we're saying is do something and then hold on a second until I'm ready to do the next thing. So what you end up with is a sequence. It's not very exciting, a sequence. It's just a little guy that I'm drawing to, we're just saying, turn on these dots in the matrix on each one of these blocks, right? But you can see that illustrates we want to draw here, wait a second, then draw here, wait, draw, and draw, and draw. So we create a sequence, and we just loop it over and over again. Well, in between each draw, what's going on? Well, we're waiting. In some capacity, we're waiting, right? Traditionally, throughout the history of hardware, we're actually delaying. What delaying is doing is blocking execution. So you have a loop, and you say, we need to move this servo from currently at 0 degrees, right, to 180 degrees. That takes time. But we can't do the next thing until we get to 180 degrees. So we'll just delay our next instruction until you're done with this one. Which means we're going to stop everything else that we're doing, and now we're going to continue. In the world of hardware, this is accepted. This has been a long time, like the how you do it. This is just, okay, you get into robotics, you understand this, and that's how you program robots. That's not how Node works, though. Not at all. You have an event loop that constantly goes, and it runs to completion and runs again, right? So, what do you do when you have a need for a sequential execution? Let's take a look at this. Hopefully everyone can see this. You see the notch? Does everybody see that? Should I play it again? Because I can if you want. Yeah, we're all good? So what happened is I was just telling it, go to this position, wait, go to that position, wait, go to this position, wait, and return. Now, in traditional processing sketch for Arduino, you might say, I'll create a servo instance, then I'm going to attach it, and then, okay, write it to this position, delay for that amount of time. That's 346 milliseconds. Okay, we're there, now write to here, and delay, right to here, and delay. So I'm saying it much faster, right? That each step blocks, stops the execution, and allows the piece of the device, the actual piece of hardware, to physically move in the real world. Because it takes time, because it's a real thing in the real world that takes time. Just as I am up here taking your time to explain this, it has to move from point A to point B, and just like when you drive down the street and you get instructions that says it's going to take you 10 minutes to get from here to there, this also has to do that, and nothing else can happen in the meantime. Which is really unfortunate if you have, say, a number of different sensors or some sort of other incoming input as well. You can't do anything or expect to be able to react to any of this information as it comes in because you've been blocking. This is how you might do something like that in JavaScript. Don't ever do this. Ever. Ever. If anybody sees what I'm doing here, I have a while loop that's blocking. Like, actually blocking for real time. It's stopping all other execution. So it's saying, this will in fact do exactly the same thing that the other script did, except it's horrible, and you don't want to do this, because what if I had more than just a servo here? What if I had a sensor that was, infrared proximity that was attempting to stop a robot from walking off the edge of the stage? Well, might not be able to do that, because we stopped it from doing anything. So we sent this information that says, move the servo. So we told it to move, and we're like, well, we're going to hold off on any execution, so see you later. And then it had no idea what happened. It just fell and busted. And then you have to go to Radio Shack and buy new parts. That's a bummer, right? So who is here is actually familiar with the effects of blocking execution? Everybody here has written JavaScript in a browser, correct? Yeah? Come on. Yeah? Yeah! Well, for your entertainment, I'm going to try to do stuff right now, and I can't, and it's broken! This is broken! Oh, just kidding, I was being blocked by this alert, because alerts block execution. Yay, we can move on now. That was horrible. It was a horrible experience for me just then.
Live demo.
I could use a set timeout, but there's some problems with set timeout. This doesn't exactly do what I expect it to do, because it wants to execute anything in what we call the stack first. And then it's going to say, well, whatever amount of time you expected me to start at. So I'm going to unwind first. Kick back, unwind. Okay, now I'm ready to do some execution. And then it goes forth. But what if you have some sort of arbitrary length number of tasks that you need to commit to, all right? Similar to our notch that was going back and forth. There was 4 or 5 different tasks there. It starts to look like this. Who thinks that looks awesome? Fucking nobody. Absolutely nobody thinks that's awesome. Because it doesn't scale and it's not composable. I can't say in my program, all right, create for me this motion and then a karate chop. I can't do that. Because what if I want to do a punch first and then a karate chop? Then I have to keep going, nesting down further. And what you end up with is an unfortunate pile of garbage. And nobody wants to look at an unfortunate pile of garbage. You might even dig even deeper and try to use Node's built-in timer ramp, right? It would get close, but it's still a timer. It still is just a timer, and is actually what set timeout in Node and set interval in Node is based on. So you can get close if you go directly to the source, but sometimes your timeouts are a little bit off, and your intervals sometimes even more off than you actually expect. But then, like me, one day you have this weird epiphany, and then you realize the process next tick is not, it's just going to run all the time. If I assign it a callback that recursively calls the same function from back within, just create a fairly minimal loop, right? So what if we also have a registry that has keys that are actually, I don't know, the current time in milliseconds, whose values are an array of task objects? We can start to create some interesting discussion there. So if you think about process next tick, can you guys see this? Yeah? Cool? Maybe I should probably pick something lighter, but I thought green was nice, like green for go. Just go, get it done. So this is obviously very slowed down, but if you imagine process next tick as a cycle, the thing that I'm creating that is, so I have a tick function that I call immediately with process next tick, and then from within, I'm recalling it, so it just creates a loop. We can then start thinking about how that applies to just stretch your imagination. These are times, starting from the beginning of time ever, right? 0. That happened a really long time ago. But just to give you an idea, I want to illustrate blocking versus non-blocking, given this zany concept I have of just a simple registry object with times and tasks. So hopefully you can see the red. So you guys see the red? Yeah? So that sucks. What happened there? It just, oh, yeah, damn, that was, oh, it stopped again. Then it tries to catch up and, we have work to do. No, we have to stop everything, and then we keep going. But if you do it in a manner that doesn't block, right? Oh, execution in the process keeps going. So if you keep your computation minimal, you could probably start to imagine it behaving sort of like this, right? Keep that process going. So that means that whatever other sensors and other hardware that are reading that asynchronous input, we're not ever blocked from having a discussion with that input and reacting to the values that we're getting, right? Awesome. This is fantastic. Everybody still with me? Nod. Or, no? Should I slow down? Should I speed up? Because you guys are like, what the hell is this over here? Get to that part. So, back to sequences. This is actually audience participation time. Because I want you guys, so I've been talking about me walking back and forth, but I want you to actually physically feel the real world around you. So everybody stand up. Seriously, everybody stand up. I want you to all now mimic what this robot's going to do. Ready? Actually, hold on one second. Just wait. I'll be right with you. Okay. Ready when I say go? Start now. Oh, this is great. All right, and stop. I now have video of you all doing this. I'm going to put it on the internet when we're done. So now you've made motions in your own physical space that took time. You had to think about it in your mind. You're like, okay, I need to have my hand up here, and this one here, and I need to do this, and I have to keep them in order. And I can't accidentally go like this, because then the program's obviously broken, and we have to go back and find out what bug caused it. So you all kept it correctly programmed to do your sequence, right? So now that you've actually physically felt that, we're prepared to move on to the next step, which is looking at how this might have been accomplished in traditional processing code for an Arduino. You would have set up these two servos, your arms, starting at 90 degrees, attach them, and then in this thing, the loop, which is going to continuously be executed on board, you say, all right, well, let's calculate where we're supposed to be. And since the two servos are facing away from each other, you can pass them the same value and they just are in the other direction. Pretty convenient, right? Until you get to here. This is the dirty little secret. That says, after we write the degrees to the servo, almost a half a second is going to be delayed, where it's going to block returning to the execution loop for the second time around. How you doing? Now, given the concept of process next tick sequences that I described to you already, you might imagine something in JavaScript looking more like this, where we just create a loop, every 500 milliseconds or so, and then set the degrees of the servo, right? Just in here, okay? Very similar. The two programs will produce exactly the same behavior. In fact, I tested this, and I have footage that you all acted along with of it. Exact same program for both of them. So, you can imagine that basically the behavior, right, is exactly the same, except for one really important thing. This never blocks execution. So if I have another sensor or something, or whatever, like, remember before I was saying, I need to know how far away I am from the edge of the stage so that I don't fall off. This one would never stop you from being able to read that incoming data. That's absolute importance. This stays alive the entire time. You never block. I already said this part. Never blocking. So, back to what we were discussing before with the notches, okay? So I'm just going to play this one more time, just so you get an idea. Now with your newfound knowledge, you can imagine that we could do this without, say, blocking execution as we had for the last hundreds of years, 200 years of mechanical engineering and computer engineering, right? Destroying history entirely today. I'm calling bullshit. So you just create a task array that might look something like this. We say, all right, well, we want the first delay, then we have this task and the second delay, and then, of course, these are actually going to queue themselves up in advance and cumulatively add up each delay so that it says, I know what to do. Take now, start from now, and just add that amount of time, and then create a task at that point with that time in milliseconds as the key. So in Process X6 is doing its thing. And of course, we can optimize on that. We could say, when there's actually nothing in the queue, don't even call process next tick. Don't call it until the next time a scheduled event gets initialized. Then kickstart it again. And if that's a single thing to wait for, a single task, that we want to just say, delay from now until 10 seconds from now to execute, we could say, there's no repeaters left, so we'll just stop the loop entirely. Just wait until we have instructions to continue again. So essentially you create this linear registry. Remember with the setTimeouts, there's nested, nested, nested. It's really hard to start to reason about where all of that begins and where all of that ends, except that it kind of starts here, kind of ends down here, or reverse that. It starts here and ends down here, right? With creating a single registry object, it's all straight down. You have, like, as I described earlier, I showed you with the demonstration of the two cycles, the blocking and non-blocking. You have the times and the tasks. So even if they're nested, it's still going to register into the exact same queue. So if I have two things that are supposed to happen, one is, 3 seconds from now, and then a second from now, I'm like, well, I have something in 2 seconds. Those will actually get queued up together. One in, obviously first in, first out order. So you end up with a straight down list of tasks that you can easily reason about. So now we'll get to the good stuff. This is the part where I make a complete ass of myself on stage. So walking is actually just a sequence of motions. Allow me. This is ridiculous, right?
Q-W-O-P.
Or, as us humans do, you just... If you break it down, it's actually like, that's one step, and that's another. They're basically the same thing. So, if we start looking at it like actual motions and like set of degrees in a position that we have a limitation, say, this is 0, 90, 180, so forth. And if I have two hip motors, or sorry, two hip servos, and 2 feet servos, you might think of it as, well, if I tilt, and then swing, and then tilt back, swing, and tilt, and swing, I could be stepping. So, let's look at that again. Ready? That's actually a few different sequential steps. Tilt is one step, swing is another step, and then the return tilt.
Full speed.
There we go. Ready? Full speed. Right? So I actually did this in my living room, and this is what spawned the whole idea of how am I going to make arbitrary sequences? This is what I realized. setTimeout not scalable and totally ridiculous and is fraught with problems, and the timer thing is way, way, way too crazy, and I'm absolutely not going to implement a delay, even though I did for about 24 hours and felt disgusting about it. No joke. It occurred to me, this process next tick thing might have feet or legs, right? So, what did I do? I made a thing walk. In case it doesn't walk right now, I got video of it walking. Come prepared, kids. And it can stop and go backwards. So, for those of you in the back that may or may not have been able to see this, I think I'd like to show you the video anyway. For those of you who missed it, yeah? Cool. So, what's the next thing we learned how to do after we started walking? We learned how to dance. Right? That's what I did when I was a little kid. I was like, hey, walking's cool. Now I want to boogie. Or maybe now I want to boogie? Possibly? I don't know. I don't know about that kind of dancing. But I'll tell you right now, this guy sure knows how that dance works. His favorite song, as you can probably imagine. The timing was terrible, but you get the idea. He really likes the movie Short Circuit. So, he was dancing to that. Here, we'll try it again. Ready?
Put your mic by the audio.
I don't know what the hell's going on. Anyway, that's my part. Thank you very much. And if you want to know more about robots, follow all these people. And there's way more, I promise, but I guarantee you somebody will ping me and say, you didn't have me in your list, but that's a good place to start. Thank you very much.